Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 40, and it is entitled Plane Mirrors and Concave or Converging Mirrors. We'll begin with a demonstration of sorts. You've probably seen amusement park mirrors where the shape of the mirror somehow distorts the image of the reflection that's seen in the mirror. What I have here are some faces that some software uses to distort. And you may have seen these sorts of things before. You bring the mouse over and then twist someone's face into some weird shape. And what this is meant to simulate is the changing of the shape of the reflecting surface. And the shape of the reflecting surface does a lot to dictate what the final image is going to look like. The shape of the reflecting surface has much to do with the appearance of the image reflected from it. So the next time you go to visit Lake Winnipesaukee or Lake Winnie, you can look at the shape of the mirror and see what kinds of images that you can get from it. In this lesson, we're treating light as if it is a wave, and we are looking at rays of light and how rays of light reflect from various surfaces. These rays of light that enter our eye somehow stimulate the nervous system to produce some sort of image that we interpret when we look at some object. The sorts of things we're going to be interested in classifying about the image in this lesson is what is the nature of the image? Is it real or virtual? What is the size of the image? Is it enlarged or reduced? And what is the orientation of the image? Is it erect or upright, or is it inverted? Mirrors are ubiquitous in our society. We use them for all sorts of things. Here are some examples of common mirrors that you may be familiar with and some that you may not be familiar with. You have mirrors in your house, in your bathroom, on the wall, above the sink, in your bedroom. You may even have a full-length mirror that you can look at yourself as you're dressing. These are examples of plane mirrors. Perhaps you carry around a makeup compact, either for putting on eyeshadow or rouge or somehow to put makeup on your face. Many of these mirrors are concave mirrors, and when you hold them in the right position and you look at yourself, you see a magnified image of whatever it is that you're looking at. When you go to the dentist puts a mirror in your mouth and looks at your teeth in order to get a good angle at the rear part of your teeth and parts of your mouth that are hard to look at. Many of those mirrors are flat or plane. Some of them are concave in order to give the dentists an image that is enlarged when they look at it. When you drive in your car, you have a mirror that's inside, that's a plane mirror, or on the driver's side, those are plane mirrors. On the passenger side, you may see a convex mirror, and the words written on the convex mirror caution, objects in mirror are closer than they appear. We're going to see that the reason for that is that the image that's produced is a reduced image, and so the image appears to be farther away than it actually is. Inside a reflecting telescope, not to be confused with a refracting telescope, there are mirrors used to handle the light that's coming in. The primary mirrors generally are concave in shape, and then there can be plane and convex mirrors that are used to reflect the light. Satellite dishes that gather radio signals are concave mirrors of sorts. They don't look like optical mirrors because their surfaces are rough at optical frequencies, but it turns out that they are very smooth at radio frequencies, and those are used to gather light. Here's an example of the largest reflecting surface in the world that's used for radio astronomy. This is a radio telescope at Arecibo, Puerto Rico. You see the dish that's down on the bottom. That is a reflecting surface that acts as a mirror for radio waves. This is a fixed dish. The size of this thing is huge. This telescope is more than 300 meters in diameter. So, in other words, 3 football fields across. Here's another telescope that's in the hills of West Virginia. It's called the Green Bank Telescope. It is a steerable telescope, radio telescope. It is 100 meters in diameter. And you can get some perspective by looking at the road that's around the telescope and some small buildings that are 1 or 2 stories high that are beside it. This is a huge telescope. and this one is the largest steerable telescope in the world. All of these are mirrored reflections, and the work that we're going to do, the ray tracing, the mirror equations that we'll deal with in lesson 54, all will apply to any of these reflecting surfaces. It turns out that there's quite a bit of vocabulary that we're going to need to deal with in this lesson. I'm not going to stop and define all of these terms, but these are going to be important ones that you need to know in context of this lesson. We will talk about each of them at some point in the lesson, but we're not going to stop to define what they are. If you need help with that, then I encourage you to look in the McGraw-Hill Dictionary of Scientific and Technical Terms, see one of your friends, come visit me, but these are all going to be important terms that you need to know. There are three types of mirrored reflecting surfaces that we're going to deal with: plane, concave, and convex. You're probably most familiar with a plane mirror. This has a flat surface. We're going to see in technical terms that the radius of curvature of this mirror is infinite. The focal length is also infinite. We're going to see that it will produce virtual upright images that have a size that's identical to the size of the object. In a concave mirror, the reflecting surface curves inward, away from the object. You can think of it as a cave, or if you want to think about belly buttons, it would be the equivalent of an innie belly button. A convex mirror is one that has the reflecting surface that curves outward. Or if you're thinking about belly buttons, it is an outie belly button. This lesson concerns itself with plane mirrors and with concave mirrors. In a later lesson, we'll deal with convex mirrors. From this point forward, we're going to focus on concave mirrors. I want to sketch a diagram showing different parts of a ray diagram for mirrors to illustrate how to sketch these ray diagrams. First of all, let's define what a ray diagram is. A ray diagram, or ray tracing, is a geometrical technique for locating and classifying images that are produced by an optical system. Many systems can have more than one optical element, but on the AP exam, you're only going to be responsible for making ray diagrams or looking at systems that contain only one optical element, the optical element either being a mirror or a lens. We're dealing with concave mirrors today. Ultimately, you're going to be dealing with convex mirrors, convex lenses, and concave lenses too. Here's an example of a complicated optical system that involves both convex and concave mirrors and lenses, but you won't get anything that is this difficult on the AP exam. This is a diagram of something that is called a Cassegrain reflecting telescope. The primary mirror is a concave mirror, the secondary mirror is a convex mirror, and the eyepiece is actually a convex lens. Here's an example of a ray diagram that shows an object. We're going to represent our objects as arrows that have a tail that sits on the principal axis, and the tip is going to represent the top of the object. You can see that the center of curvature and the focal point of this mirror are shown, and there are only two of the infinite number of rays that emanate from this object that reflect from the mirror. This particular image that is produced by this object is a real inverted reduced image. The nature is real, the size is reduced, and the orientation is inverted. Now I can change the position of this object, and when I do, I change the position of the image. And there comes a magical point at which the object and the image are exactly the same magnitude and height. The image produced by this particular position is real, and it's the same size as the object is. As I bring the object closer and closer to the focal point, I produce a real image that is enlarged until I get to the focal point. And when I do that, then something magical happens, and the image stops being real and becomes virtual, and the orientation of the image changes as well. This is for a concave mirror. Convex mirrors will have different things happen. Convex and concave lenses will have different things happen to them as well. This is a special case for the concave mirror. At the back of this lesson, the last pages of the lesson, there is a summary in a table that shows what happens when the object is at certain positions with respect to the mirror. So let's sketch an optical system, and sketch a ray diagram. Here is a concave mirror with its reflecting surface pointed toward the left. Indicated on this is a large central line that is called the principal axis of the mirror, and on that principal axis is the focal point of the mirror and the center of curvature of the mirror. The principal axis passes through the vertex of the mirror. You could think of the vertex as the center of the bullseye of a mirror and sits on the principal axis. In my diagram, I have tried to make these marks along the principal axis 1 centimeter apart. I don't know what they'll look like on your computer screen, but when I sketched them, I used a ruler and made them 1 centimeter apart. On this principal axis, I'm going to place an object. I have made this object 3 centimeters tall, and our job is to try to locate and classify an image that's produced by this object. It turns out there's a mathematical relationship between the center of curvature and the focal point that will help you solve some of these ray diagrams. It turns out that the focal point is equal to half the distance away from the vertex of the mirror that the center of curvature is. So you could say the focal point is 1/2 of the center of curvature of the mirror, or the center of curvature of the mirror is equal to 2 focal lengths. There are an infinite number of rays that leave this object and hit the mirror and produce an image. Each of those rays, when they hit the mirror, is going to obey the law of reflection. And if I were going to be very careful, I could measure the angle of incidence and the angle of reflection and produce an image. But that takes a long time that you don't have on the AP exam. And so what I want to illustrate are 3 principal rays that you draw that produce the reflected image. And from any 2 of those 3 principal rays, you can locate where the top of the image is and then classify the image according to its nature, its size, and its orientation. Before you actually start sketching these rays, you need to sketch a plane of reflection that intersects the vertex and is perpendicular to the principal axis. And all the ray diagrams, the rays should reflect from that plane of reflection. If you're following along in your textbook, then the 3 rays that I'm going to draw are described on page 340. Ray number 1 is a ray that leaves the top of the object and travels parallel to the principal axis. It hits the plane of reflection and then passes through the focal point. So there's the incident ray from the top of the object of the first ray, and there's the reflected ray. So we'll call this ray number 1. The second ray leaves the top of the object and passes through the focal point until it strikes the plane of reflection. After that, the reflected ray then travels parallel to the principal axis. There's the reflected ray. That ray, after it hits the plane of reflection, travels parallel to the principal axis. And now for ray number 3. Ray number 3 leaves the top of the object and passes through the center of curvature, C. That ray strikes the mirror at normal incidence and it reflects backwards on itself. So there's the incident ray, leaves the top of the object, it travels through the center of curvature, and it goes to the plane of reflection. Now, if that ray happens to strike outside of the mirror, I just find where that ray would hit the plane of reflection. Then this ray reflects backwards on itself. So the reflected ray is going to come straight back. It's going to lie on top of this ray, this incident ray. So it's going to travel backwards like that. Now these 3 reflected rays from ray number 1, ray number 2, and ray number 3 intersect at some point. And the place where they intersect is the place where the top of the image is. And that intersection point is right there in this particular diagram. That point represents the tip of the image arrow. The tail of the image arrow sits on the principal axis. And so I'm going to sketch and label that arrow as the image arrow. Now that I have sketched this image, I want to classify this image according to its nature, its size, and its orientation.